Welcome to Lecture 24. In this lecture, we're going to finish up Chapter 29 by talking about magnetic material, and then we'll move on to Chapter 30, which has some really neat stuff. We're going to circle back around now to the beginning of the chapter, where we started off by saying that moving charges make magnetic fields. Ampere actually theorized that molecular current loops are responsible for all magnetic phenomena, so let's explore that idea a little bit. Let's think about any atom at all. An electron orbits the nucleus. So let's say that the electron comes around in this direction. The current direction would be opposite because that's the direction that positive charge would flow. So if electrons orbit, that's a moving charge over time. That's exactly the same thing as a current. That little current loop then has a magnetic moment. That means that every atom actually acts as a little tiny magnet, each with a north and a south pole. In many materials, the moments tend to cancel out, and we will discuss that on the next slide. But first, we'll talk about the fact that the electron orbiting the nucleus is not the only motion in an atom. Electrons also tend to spin around their axes. So they spin around in circles like this. So let's write that down. Electrons also spin. A little rotating or moving ball of charge also makes a magnetic field. So the charge is moving, that still makes a magnetic field. So rotating charge makes another magnetic moment. Also has symbol of mu. Most of the electrons in atoms, they do act as little magnets, but most of the electrons are actually paired up. You probably learned that in a chemistry class. That means that overall, most of the magnetic moments cancel. So most electrons are paired. The ones that are paired up, the mu's cancel. But some of them are actually unpaired, and that leaves an overall net magnetic field or net magnetic moment. That's pretty cool. So some are unpaired. That gives us a net magnetic moment. That's a pretty interesting result, and we're going to get into talking about that on the next slide. First, I'll just give you a little homework question to try. Can you find the magnetic moment of a hydrogen atom? In a hydrogen atom, we know that the electron orbits at a speed of about 2,200 kilometers per second, and the radius is 53 picometers. See if you can use that information and find the magnetic moment of the hydrogen atom. Thinking about those electrons and whether they're paired or unpaired leads us to permanent magnets. Now, our picture on the left, this represents most materials. In most materials, the electrons that are left unpaired, they actually point, the magnetic moments point all over in random directions. That means if we add up the total magnetic moment, we add up the magnetic moments due to each little one, what we end up with overall is that a net magnetic moment is zero or pretty close to zero because everything cancels because they point in random directions. Not every material is like that. In some materials, the magnetic moments line up. Those materials are called ferromagnetic. That's what we have on the right. Ferro means iron, and these materials are probably called ferromagnets because iron was probably the first magnetic material studied. In ferromagnetic materials, the materials all have the magnetic moments aligned. So they all point in the same way. That results in a net magnetic moment. So the net magnetic moment is not zero. What I find kind of neat about this is that when you pick up a magnet and you stick it on your fridge, you're actually seeing the effect of spinning electrons. I think that's kind of nifty. So those little tiny things that you can't see that are spinning around, that's what makes it stick to your fridge. Now, most materials don't have the whole thing perfectly aligned like the picture showed on the previous slide. Mostly they have various areas that are each aligned. Each area of alignment is called a domain. So each of these little bits here are all aligned, and that's a domain. Each domain has its own magnetic moment. You can actually change the moments of the domains pretty simply just by dropping a magnet. If you drop a magnet often enough, it will lose all of its alignment and become permanently demagnetized. On the flip side, you can also increase the magnetism by inducing more alignment in each of the domains. That's how an electromagnet works. If you make a magnetic field, like with a solenoid, and bring it close to a ferromagnetic material, for example, a lot of solenoids, we have a solid iron core, the ferromagnetic material will have the domains get all lined up and the material will get fully magnetized. Okay, so that's just a snapshot of permanent magnetic material. There's a lot of interesting stuff, but we're going to leave chapter 29 here and then move on to chapter 30.